discuss the one last very abstract result from here. So I've got C, the usual. So C is a Gorenstein projective, of course, Gorenstein curve, and H on C, a divisor. And so I say that our sufficient condition for H to be very ample two slightly different alternative things. So one is for every B in C, this is this previous thing, generically Gorenstein. For every generically Gorenstein subcurve in B, H times B is greater than or equal to 2PA plus 2PA of B plus 1. Or, so this is just, I can slightly weaken this condition, or H times B is greater than or equal to 2 PAB, and there does not exist a subscheme Z in B of length 2. So this means either two separate points or a point and a tangent vector at the point with IZ times OB of H is isomorphic to omega B. Okay, so in this statement, this is the first theorem in the paper. Let's just read the statement. So, of course, I have in mind that the case the case C where C is arbitrarily non-reduced and so on. But if C is a non-singular curve, this is saying that the degree of H is greater than 2g minus 2 plus 3. So this is 2g minus 2 plus 3. Right? And so that's exactly what you need in order that given any 2 points, of the curve, if I subtract off the 2 curves, I still get a regular divisor. So this is just, this is, so to speak, the trivial thing for a non-singular curve. Right? And so, what's the idea here? So if H fails to separate Z, right? This means that H1 of IZ of OC of H is not equal to 0. Right? And so, by this property, so then there exists a homomorphism S going from IZ OC of H into omega C. Right? And this necessarily factors through IZ times OB of H mapping into omega B. Yeah, so what am I doing here? First of all, I'm saying this HI, this H1 here, is dual. So this is possibly singular sheaf. This is not a locally free sheaf. So when I say Serre duality, I should go from the hi to the corresponding x n minus I. In this case, the corresponding x n minus I is just a hom from here into here. Yeah? So this guy being non-zero is just the same as their existing homomorphism there. Right? Now this homomorphism might be generically injective, in which case B is equal to C and we've finished. Right? So either in this case we get a contradiction, because the degree of this one is 2p minus 2, and the degree of this one is this. Okay? Or it's possible that S is killed by some sheaf, that S doesn't live on the whole of C, but only lives on this B. So in that case, I define the annihilator of S to be some sheaf of ideals. That sheaf of ideals defines a curve B. Then I've got here a homomorphism now from OB, from a sheaf on OB, from a sheaf on B into omega C. It necessarily factors, by this automatic adjunction, necessarily factors through a sheaf of OB modules, through this thing here, which is hom of OB into omega C. So this is just exactly the same use of duality that I had before. Yes? And so, you know, and then the sheaf, the curve there is generically Gorenstein because it's the smallest, you know, B is the smallest, B is the curve on which this S is supported. So this S here vanishes on some part of the curve C, and then you divide out by the annihilator of it, and this is where it's non-zero. And so this map here is now injective. It doesn't vanish on any component of B. Yeah, and so either I've got you know, in this case I'm getting a contradiction. In this case I'm getting the positive result that you know, I have this thing which might be a hyperelliptic kind of thing. Right, so this is telling us a more precise result. It's saying if I've got, you know, so here's my curve. I've got x and y on it, or I've got, you know, x and y on it. That's z. Right? These z's, the linear system H on the curve is contracting this z to a point if and only if it's lying on a, the z is contained in a subcurve B, which is generically Gorenstein, and with this inequality. Right? So this is a very, very precise result. It's stated in this language of abstract curves. Okay, so let's stop doing the abstract curves and start doing the surfaces that I'm interested in. So I think I stated this result before, but let me state it again. So X, canonical surface. So this means it has Duval singularities, and Kx is ample. So assume, this is in order to have a self-contained theorem, assume that h1 of 2k of x is non-zero, is 0. Right, so if we're in characteristic 0, this is automatic by Kadara vanishing. It's also true unconditionally in characteristic P, but I'm not going to bother you with the details. Right? So actually this assumption is not an assumption at all. This is, but it is. I don't want to get involved in very, very complicated things about surfaces in characteristic P. Okay, then the statement is that mkx is very ample for m greater than or equal to 5, and it's also very ample for m greater than or equal to 4 if you assume also that k squared is greater than or equal to 4, greater than or equal to 2. It's also very ample for m greater than or equal to 3 if Pg is greater than 2 and k squared is greater than or equal to 3. Okay, so these are pretty weak conditions, right? And they're certainly necessary. They're certainly necessary because, there's this example x10 in weight projective space 1, 1, 2, 5. So, this would contradict this. If you don't have 5 here, this has k squared equals 1. So if you don't have k squared equals, if you only have k squared equals 1, then this statement 4 is just not true. And then there's the x8 in weighted projective space 1, 1, 1, 4. This is the double cover of P2 branched in a curve of degree 8, right? So that has k squared equals 2. And so it has Pg equals 3, but k squared equals 2. But the statement with m equals 3 is no good. No, I'm sorry, k squared equals 2. Said it exactly wrong. Okay, so this result I'm stating is really very close to the best. So the paper FHR also contains, and other people. So Francia was here, and Reid was here before us. Of course, Bombieri and Ramanujan and Kadara were there also. So also gives an exact obstruction for 2k to be very ample. Right, and it's useful to say this because then you start understanding what the real substance of surface geometry is. So if you assume, for example, that Pg is greater than or equal to 4 and k squared is greater than or equal to 10. So assume then 2k contracts a z of length 2 to a point if and only if z is contained in a curve B, so two cases, k squared equals, k times B equals PA of B equals 1, or k of B equals PA of B equals 2. Now these cases, they can be stated together, but basically they're quite different things. Okay, so what's happening here? So in particular, 2k is birational, except for x with a genus 2 pencil. Right. So this is something that comes up from time to time. So here, I'm assuming this. So I'm avoiding, the initial, the first 100 cases for these invariants, where they're small, really small invariants. Then apart from that, the linear system 2k is always a birational. It's always a birational map, except for the case where x has a genus 2 pencil. Okay, so it's useful to say what these cases really mean. So this means on the non-singular minimal model, s to k to x. This b is a curve with PA of b equals 1 and b squared equals minus 1. Right, so if you do that, here's the curve b. He's got self-intersection minus 1. He's really an elliptic curve. It would be an elliptic curve if you were non-singular. And then when you look at kb on it, when you look at kx on this b, this is a divisor of degree 1 on an elliptic curve. Right, a divisor of degree 1 on an elliptic curve. So if you take twice the divisor, he moves in the linear system, but he still maps that curve 2 to 1. Right, so there's a curve there on which you can't hope to have 2k very ample. On this curve b, 2k is certainly, even if it maps surjectively to the linear system restricted to the curve, then it's going to map the curve 2 to 1. Right, and this one is basically similar. Here, this means that b squared equals 0 and PA of b equals 2. So kx times b is 2. Right, and the story for this one is that this is a curve of genus 2. And kx restricted to the b is kb. Right, so everybody knows a curve of genus 2 is this curve C6 in weighted projective space 1, 1, 1, 3. So, I'm sorry, always get carried away. It's a double covering of P1 with 6 branch points. So this is just the curve of genus 2. And so, it has this G12 on it. The G12 is the canonical class. Right, and if you take twice the G12, it still doesn't separate these points because I don't have the 3 yet. Right, so the twice the canonical class here is taking this curve of degree 6 and it's mapping it 2 to 1 to a conic in the plane. Right, and so if I have a whole pencil of these curves of genus 2, then, or when I do the 2 canonical map of the surface, it has to do this 2 to 1 map on every curve in the pencil. And so the 2 canonical map is certainly not birational. But the statement here, I'm not going to prove this today. The statement here, the statement is due to various people. I mean, Bombieri knew it perfectly well, but it's basically came out very clearly in the work of Francia. The point here is that this is also a this is the only exception. This is the only infinite family of exceptions. So if I have a surface with fairly big invariance and the 2 canonical map is birational, then necessarily I have infinitely many of these curves. And the only way this can happen is if I have a pencil of curves of genus 2. Okay, so this is there's a nice conclusion here. This is a really nice theorem. I should warn you that the proof of this is, well, the way we do it is fairly complicated. It's quite tricky to, about 10 pages of the argument's taken up with just this last thing. So, so how am I intending to prove this? Well, the idea of the proof is to reduce it to this sort of basically coarser result about any curve and a linear system on it which is fairly big. And so what we want to do, and I'm not going to get this completely right, is is think of, so I want to look at mk. So, you know, think of the m as being 5 or 4 in these two cases. And I want to take, inside here, I want to take a curve which is of the form m minus 2k. That's going to be called C. And then plus some other curve. That's going to be called, you know, some other. Right, and then I want to say, well, I can take the mk and I can restrict it to C, and this is surjective. The restriction of this linear system to the curve C is surjective because I have this condition, this assumption. Right, and you know, I can arrange that this condition degree of mk restricted to b is greater than or equal to 2pa plus 1. I can usually right, and so, you know, I have this linear system and I can restrict him to these two, separately to the two guys, and you know, sort of work around. And so, you know, there's no, we're not doing anything really very, very precise here. We're just doing what you have to do to prove the theorem. So I'm afraid this is now not going to be especially well prepared. It's always easy to prepare the first half of the talk and hard to prepare the second half. So, you know, the name of the game we're doing here is we're taking this linear system and we're breaking him up into 2 pieces or sometimes 3 pieces. Right? And so there's a, I'm just going to you know, consider the actual lemma we use. So there's this lemma 4.1 in the paper. It's saying I've got H, so now X is any irreducible scheme. And I have H, the Cartier divisor. Right, so, you know, those are examples. So I'm going to, I'm thinking of H linearly equivalent to D1 plus D1 plus D2 with D1, D2, non-trivial linear system. So these at least start moving. Right, and what I want is that, or the same with D1 plus D2 plus D3. I don't really know why we do this, but you know, I'm trying to get over the general idea rather than the special details. Okay, and suppose also A, that H naught of X of H maps to H naught O of these DIs. Surjective. Right, so I mean, in this case, I've got a divisor H on X, and he's broken up as 2 pieces. Right, and I certainly know that the H restricted to each of these is surjective. And that B, H restricted to delta I is very ample on every delta I in di. So, you know, I mean, in the applications, as far as I can see, you know, for example, I've got this MC, MK looks like C plus C primed. So under either any of these sets of conditions, we have a decomposition like this or a decomposition like this, where these are non-trivial linear systems. So here I've divided it into two. Right? And we know that this map is surjective. Right? For example, in this case, if I'm restricting these guys to this guy, we know he's surjective because the h1 of 2kx is 0, etc. Right? And we also know that h restricted to each of these curves. So now I take any curve in this linear system, not just the fixed curve C. I take any curve in that linear system, and then I say that the h restricted there is very ample. Right? So, you know, I'm doing in the application, I'm just going to be using this criterion. Right? I've arranged for the h here. The h is already some multiple of the canonical class, and the b is something in C, and so we'll win this. Right? Then the conclusion is that h is very ample on X. So, you know, the idea of the proof is just, you know, take X and Y in X. So if X, so you know, there are different cases here. They could be if X is not equal to Y, if they're separate, if they're distinct points and they both belong, X, Y, both belong to delta I. Right, then this one is going to be very ample, and so then H, sorry, I've got H linearly equivalent to, so H is linearly equivalent to delta 1 plus delta 2, right, where this one is very ample. This one is separates X and Y. And this one here is disjoint from X and Y. Right. So, you know, I mean, it'll also happen sometimes that one of these x's, for example, is a base point of this linear system, and then the other one is infinitely near to it. And then I have to argue about whether or not these delta i's are separating the points. But anyway, this is only the idea of the proof. It's so, you know, I mean, it's just a messy little thing. I'm taking the linear system that I want to prove is very ample on the surface, and I'm saying, well, I can restrict him happily to any subdivision of this curve, and he'll be very ample on the different parts. So this is the that was a proof of the main. So proof, description of the proof of the main result on pluricanonical embeddings. So, you know, maybe I won't get the proof exactly right, but I hope I'll just sort of describe. So I'm going to argue on, here's X, here's S, here's C. So I'm thinking of the C as being in M minus 2K. Right. And so, you know, the obvious thing that you can say is that H naught of MKX maps surjectively to H naught of OC of MKX restricted to C. This is surjective. So that's the assumption that H1 2KX is 0. So also OC of MKX is very ample on C. Okay, so so now I'm talking about this theorem. So by the curve theorem, so I'm giving a description of the proof here. Proof by the curve theorem. It's enough to have MKX B is greater than or equal to 2PA B plus 1 for B in C. So of course you notice the in this case the X is possibly a little bit singular. On the other hand, the X is only singular at finitely many points. So every curve on X has this generically Gorenstein property. Right, so apparently I can write this as being Kx restricted to B plus Kc restricted to B. Right, so this guy is greater than or equal to 1 just because the Kx is ample. So what I want is apparently Kx times C is greater than or equal to 3, which we're going to get by assumption. We're going to get by these assumptions in the different cases. So that's in the case that if B equals C. And we also need a degree of OB of C, OB of Kc minus the degree of omega B greater than or equal to 2. Okay, so I want to get this to be greater than or equal to this 2. So twice the degree of this plus 3. Right, so I'm winning 1 from here, and I'm going to win 2 from here. Right. So the point is just that if B equals C, I get this KX times C is greater than or equal to 3. This is by the assumptions in the 3 cases. In the 3 cases. In these, what I mean is these 3 cases. right? And then if B is strictly contained in C, I'm going to get kx times B is greater than or equal to 1, just because it's ample. And the other guy, kc plus B, kc restricted to B is greater than or equal to 2pa of B minus 2 plus 2 by numerically 2 connected. Okay, so there's a little issue here. There's a little issue that's you know, here I've got S to X. Here I've got the C, and I know here that if I take f upper star of C, that this here is numerically 2 connected and 3 connected, except for minus 2 cycles. Okay, so this was I've discussed this. I've discussed this twice before. This guy here is Neff and big on a. This guy is Neff and big on a surface, and also he's closely related to the canonical class of S. He's either canonical class or twice or 3 times the canonical class. And so you know, you start looking at this C is A plus B, and then you start worrying about A squared and AB and B squared, and you find that AB is greater than or equal to 1, and AB equals 1 is a very, very special case. Anyway, I have described this already, and it's it basically goes back to before our time. So, but there's still a problem here, which is so there's a lemma that says f upper star C k connected implies C is k connected, and f upper star C k 2 connected and 3 connected except for minus 2 cycles implies that C is 3 connected. Okay, so you know, what do you have to do? So you know, suppose f upper star. Suppose that so you know you know the point I have to I'm using this word 2 connected and 2 connected. And, I'm using k connected. This is on a non-singular surface, so this is the A plus B stuff. Whereas here, this is the omega B and the Kc restricted to omega B stuff. So the definitions are different here. I mean, there's nothing. And so anyway, what you have to do is, if B is in C, in X, then you have to somehow or other go to the resolution S, and write here. I write f upper star C is, you know, A plus B primed. And you can take B prime to be the birational transform, and then you can mess around. So I'm not giving the correct proof here, so mess around. I mean, it is quite messy, actually. Okay, so there's something to be proved there. I think I'm going to leave it at this. If I try to explain it anymore, it'll I have to start reading the paper more. So as I said, I'm intending to talk on a different subject next time. I don't know what else I should do here. So you know, the thing that remains is to just check that I can make these linear systems. I can, for example, in these three different cases, I can arrange for this C here to pass through any two general points. So this is the point of this messy little lemma, right? So you know, if I'm in, for example, if I'm trying to prove the case m is greater than 5, then the thing that's here is 3k. So you write down the Riemann rock for 3k, and you find that it's got some dimension. You know, it's chi, which is at least 1 plus k squared plus 9k squared. So it's something like 10-dimensional. So I can certainly force it to pass through any 2 points of the surface. And then these kind of arguments show that the linear system mk restricted down to that curve, and then restricted down from the curve to the cycle of 2 points is surjective. So the linear system separates any 2 points on these curves. Okay, anyway, you know, if you want to see the details, then this paper is something that you can probably spend a few weeks studying in detail. Yeah, I wish I could explain it better, but I haven't prepared it all that well. Okay, so I'm going to leave it at that for today.